Good morning, students. So today we'll be discussing the last topic of this unit, that is the plastic constraint factor. So till now we have seen the sizes of the plastic zone, that is RP. So this we have seen for theta equal to 0, that is using Irwin's correction factor. Second one is Dugdale's approach, right? And also we have seen this RP when theta is not equal to 0 for the plane stress and plane strain condition. So in both the conditions we have seen for von Mises and Tresca criteria. So that means what? Till now whatever we have seen was just focusing on this RP, that is the size of the plastic zone. So today we shall see the concept what is called as plastic constraint factor. It is also defined as PCF. So it can be said as the ratio of the maximum stresses which are developed in the component to that of the yield stress of the component will give you the plastic constraint factor, that is PCF. So here we shall obtain the expression or the size of the plastic zone using this PCF. So let us see how to determine the size of the plastic zone using the plastic constraint factor. So let's begin with this lecture. So you can just take down few lines over here before we start with the derivation. The maximum stress in a plane strain plastic zone can be as high as 3 times the uniaxial yield stress. So the ratio of this maximum stress to the yield stress is called as the plastic constraint factor, that is PCF is equal to sigma max by sigma ys. Okay. The PCF for plane strain crack problems can be estimated as follows. So here we assume sigma 2 is equal to n times sigma 1 and sigma 3 is equal to m times sigma 1. So here we have represented the other two principal stresses, sigma 1 and sigma 2 and sigma 3 in terms of sigma 1. Now for von Mises stress criteria, that is we have seen yesterday in the previous class. So as per von Mises criteria we have sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square is greater than or equal to 2 sigma ys the whole square, right? So now in this we shall substitute for sigma 2 and sigma 3 in terms of sigma 1. So we can write this as sigma 1 minus n times sigma 1 the whole square plus n times sigma 1 minus m times sigma 2 sigma 1 the whole square plus m times sigma 1 minus sigma 1 the whole square is equal to 2 sigma ys square, right? So we have written this in terms of sigma 1 completely. So from this terms we take the sigma 1 term outside first, that is sigma 1 square in the bracket we have 1 minus n the whole square plus sigma 1 square into n minus m the whole square plus sigma 1 square into m minus 1 the whole square equal to 2 sigma ys square. So here taking sigma square outside and we shall just open each of these square brackets. We have a square plus b square, that is 1 plus n square minus 2ab, that is 2n for this. For this it will be n square plus m square minus 2nm. So here I am putting them in small brackets so that simplification will become easy. So plus m square plus 1 minus 2m is equal to 2 sigma ys square. Clear? So now here what we do is we just see which terms get cancelled here or which term can be clubbed. So you have one n square over here, second n square over here. So you can write this as sigma square in the bracket 2n square. Okay, that is this n square and this n square I have clubbed. Then we have m square plus 2m square. So I have clubbed this m square and this m square, minus 2n minus 2m minus 2n minus 2m minus 2nm. So I have taken minus 2n minus 2m minus this one, and 1 plus 1 is 2. So that is plus 2 will be equal to 2 sigma ys square. So taking this 2 outside, so we have 2 sigma square in the bracket n square plus m square minus 2n minus 2m minus 2mn plus 2 will be equal to 2 sigma ys square. So this 2 and this 2 gets cancelled. So ultimately we get sigma square or sigma 1, here it is. I've taken this as sigma. So it is sigma 1. So sigma 1 square in the bracket we have 1 plus n square plus m square minus m minus n minus mn will be equal to sigma ys the whole square. So now we have the plastic constraint factor, that is sigma max upon sigma ys. So we shall write the equation for that. So plastic constraint factor is sigma max upon sigma ys so this can be squared. So I can write this as sigma max square upon sigma ys square. So if we take the maximum stress as 1 in this example, so this becomes 1 upon or you can write this as the maximum stress will be sigma 1 squared over here. So sigma 1 square and sigma ys square is sigma 1 square into 1 plus n square plus m square minus m minus n minus mn. So this square and this one gets cancelled. So ultimately sigma max upon sigma ys will remain as 1 by root of 1 plus n square plus m square minus m minus n minus mn. Clear? So we can say PCF can be written as 1 plus n square plus m square minus m minus n minus mn raised to minus half, because this denominator goes into numerator, and we can write this as minus half. So here the above equation or the equation which we have got over there, it enables to calculate the plastic constraint factor at any location of the crack tip. So from the stress field equation, that is sigma 1 is Ki upon root of 2 pi r cos theta by 2 into 1 plus sin theta by 2, and sigma 2 is equal to Ki upon root 2 pi r cos theta by 2 into 1 sin theta by 2, and for plane stress sigma 3 is 0, and for plane stress mu into sigma 1 plus sigma 2. So we get sigma 3 as 2 mu Ki upon root of 2 pi r into cos theta by 2 for plane strain condition. We shall now calculate what will be the value or the equation for m and n, the two constants which appear in that equation. So here you can take down this statement. The above equation enables to calculate the plastic constraint factor at any location of the crack tip, From the stress field equation, we have sigma as Ki upon root of 2 pi r into cos theta by 2 into 1 plus sin theta by 2. Then we have sigma 2 is equal to Ki upon root of 2 pi r into cos theta by 2 into 1 minus sin theta by 2, and sigma 3 is equal to 0 for plane stress condition, and this is equal to mu into sigma 1 plus sigma 2 for plane strain condition. And this we have already seen in the previous derivation, that is determining the plastic zone size for when theta is not equal to 0. In that plane strain condition, we can get the value of sigma 3 as 2 mu Ki upon root of 2 pi r into cos theta by 2. Okay. So this is what we get the equation for sigma 1, sigma 2 and sigma 3. So now we can write n is equal to sigma 1 upon sigma 2, because this is sigma 2 upon 1. Okay, before this we can take this as the equations which we have taken first. Sigma 2 is equal to n times sigma 1, therefore n is equal to sigma 2 by sigma 1. So here this equation divided by this equation, so that Ki upon root of 2 pi r cos theta by 2 gets cancelled. So ultimately what remains is 1 minus sin theta by 2 upon 1 plus sin theta by 2. Similarly, sigma 3 is equal to m times sigma 1, therefore m is equal to sigma 3 upon sigma 1. So here again this Ki upon root 2 pi r and cos theta by 2 gets cancelled. So what remains is 2 mu upon 1 plus sin theta by 2. Clear? So here we have got this for plane strain condition, and m will be equal to 0 for plane stress condition. So why it will be 0? Because sigma 3 is 0, so 0 upon any number will be 0, so m will be 0 for plane stress condition. So next we shall see for plane stress when theta is equal to 0. So now here we have the terms theta. So first we shall take plane stress when theta is equal to 0. We have n will be equal to 1, because this will be 2 and here also you will have 2. So minus of sin theta by 2, we can write it as 1, and when theta is 0, this will be 0. So ultimately what remains is 1, and here also sin 0 is 0 and what remains is 1, so 1 by 1 will be 1. So n will be equal to 1, and for plane stress m is 0. So what will be the plastic constraint factor PCF? So that will be equal to 1 plus 1 minus 1 raised to minus half, and this can be written as 1. So when theta is equal to 0, the plastic constraint factor will be equal to 1. That means what? Sigma max, or the maximum stress that is induced in that component, will be equal to the yield stress of that component. That is, the yield stress itself will be the maximum stress when we have the plastic constraint factor as 1. For plane strain condition, when theta is equal to 0, for plane strain condition, when theta is equal to 0, n will be again equal to 1. And what will be m value now? For plane strain we have this. So this term becomes 1 because sin 0 is 0. So 1 plus 0 is 0. So in the denominator you have 1. And in the numerator it remains is 2 mu. So you can write m as 2 mu. So plastic constraint factor, that is substituting n and m in that equation which we have derived for plastic constraint factor, we get this as 1 plus 1 minus 4 mu square minus 2 mu minus 1 minus 2 mu raised to half. So here this minus 1 and this plus 1 gets cancelled. So for most of the cases we take mu as 1 by 3. Therefore the value of m will be equal to 2 by 3. So substituting now this m in this equation over here, we get this mu we are substituting over here in this equation, we get PCF will be equal to 1 plus 4 by 9 minus 2 by 3 minus 2 by 3 raised to half, minus half. So this upon simplification we get 3. So with this what we can say is sigma max upon sigma ys is equal to 3. So this implies that the maximum tensile stress that is developed here will be equal to 3 times the yield stress of that specimen or the component. So if you multiply this plastic constraint factor into the yield stress, it is also called as the effective yield stress, that is sigma ys dash. So we can say sigma ys dash will be equal to sigma max. So sigma ys dash will be nothing but 3 times the yield stress, that is sigma ys. So here we get that condition. So what is that condition? Sigma ys into PCF is nothing but sigma max, and this is called as effective yield stress sigma ys dash. Therefore we can say sigma ys dash will be equal to 3 times sigma ys. Therefore substituting the above equation in plastic zone correction factor, that is we have seen this plastic zone correction factor Ry is equal to, this correction factor is not the Irwin's but it is the actual equation for the size of plastic zone, that is Ki square upon 2 pi sigma ys the whole square. So now in this equation we substitute this effective sigma ys, that is effective yield stress. So we can write this as, let Ry be equal to Ki square upon 2 pi sigma ys dash the whole square. So this is let, so you are considering this. So upon simplifying this we get Ry is equal to Ki square upon 18 pi sigma ys the whole square, and let us take this as equation number A. So in a practical case, the average PCF or plastic constraint factor is much lower than 3. So it is approximated to be equal to root 3 according to Irwin's theory. So sigma ys dash can be taken as root 3 sigma ys, and in that case what happens to Ry, we have the equation just changes. So instead of 18 in the denominator we get this equation, that is Ry will be equal to Ki square upon 6 pi sigma ys the whole square. So this you can take as equation number B. The value of Ry is root 3 according to Irwin's theory. So you can say it is 3 times the plastic zone correction factor for equation A. So whenever you multiply A with 3, that is you have 3 times equation A, you get equation B. That is using the Irwin's theory. So that's it, and with this we end this unit, that is size of plastic zone. So in the next lecture I shall start with stress intensity factor. So already I have shared the notes with you all for this unit. So you can refer to the notes and you can watch this video for understanding what are the steps involved in the notes. So that's it for today in this lecture. So in the next lecture I shall start with the stress intensity factor.